Hey everyone, it's Mr. Anderson coming to you again. We are in our second section of section 2.1, chapter 2.1, chapter 2, first lesson in our CPM, Common Core Algebra book. And our goal today is to do the deep dive on slope. And we are going to talk about what makes slope change, right? How do I measure that steepness? And, what might have an impact on that. So what things can we manipulate and toggle in order to make a line steeper, a line less steep, etc. So previously we determined the growth rate and starting value using those tiles in our last lesson. If you need to back up and look at 2.1.1 again, go ahead and do so. And we made a table and an equation. In this lesson, we're going to talk about manipulation of that slope. So our questions that we want to focus on today: what makes a line steeper? What makes a line less steep? All right. How is growth related to steepness? And then where do we find that starting value? Where's it located on a line? Where's it located in a table, et cetera, et cetera? So we're going to look at those things today. And we've got in 2.11, this is our first core problem that we're going to start today. We've got a table that's representing a function down here on the right hand side, and we're going to go ahead and write the equation of that. And I need to know two things. I need to know a starting value, and I need to know a slope. And you saw this if you watched the function video. You saw me set up things using maybe something you've seen before, our slope-intercept form, our y equals mx plus b format. And the way that it's easiest to do this is maybe consider your M and your B as blanks. And these are things that we're going to have to fill in. And the information is given away in the table or on the graph. And we'll look at graphs today as well. And what I'm looking for in this particular case is, how is this growing? Now, the first thing I'm checking is my figure number, my dependent variable. My independent variable, my x's. Those particular things are growing by 1. And that's good. Because if that's the case, if I go from 0 to 1, 1 to 2, 2 to 3, etc., I'm counting by ones. It also means that my denominator, my slope, is going to be 1. And it means my slope can maybe very easily be evaluated as a whole number. And we'll get to this in a little greater detail as we look at graphs in a moment. But take special note that we're counting by ones in the figure number here. The next thing that we're going to go ahead and do is we're going to look at the y values, the number of tiles that we might have. And here, because I'm counting by ones, is where I'm looking for that change. So the question that I would ask is, what am I going up by there? I count from 2 all the way up to 7. What am I climbing by? And is that the same as I count from 7 to 12 and 12 to 17 and 17 to 22? And the answer is yes. And what is that? We're growing by 5, or adding 5 each time. Now, here's where I said, hey, we're counting by ones here, right? So this is maybe adding 1 each time. Some of you guys remember that your slope is your rise over your run, your change in x over your change in y. So if you want, go ahead and write that here, right? 5 over 1 is the same thing as 5, and I'll just make a little note. Hey, that's the exact same thing. I'm trying to star that there. That's the exact same thing as 5 over 1. I just wrote it as an integer instead of a rational expression. But then the next thing I need is the starting value. This is back up to that idea like in figure 0. Okay, in figure 0, how many tiles did we start with? And that's answerable by looking at the table. Everybody check this out with me. Figure 0, I'll make my highlighter a little thicker. Figure 0 is right here. And how many tiles do we have to get started? And that answer is 2. Now you might be questioning, you might say, but Anderson, I don't know what this looks like. I don't know what this tile pattern looks like. And honestly, that's okay, right? What we're going to learn pretty quick is if we're going to consider these as tiles, it doesn't really matter what it looks like as long as we understand how we're growing. And in this case, we start at 2, we're growing by 5 each time. We've got a pretty unique function here, and we can represent that using the table. We can represent it using the growth, the tiles. We can also represent it using this thing right here called an equation. And that's going to work out pretty well. And note, I just referenced some prior learning, something we probably saw in pre-algebra. and that is that y equals mx plus b format, and I plugged in m and b. Okay? In this particular case, you might already know the answer to this, but it's saying, hey, does it appear to be a function? If so, write this equation in function notation. If not, explain why. Well, two things. Does every single input have an output? And the answer is yes. In this particular table, and that's all I can see right now, in this particular table, grab a different highlighter here. In this particular table, I can see that every single one of these x values is sent to a y value. And that's good. That means we are onto, right? That means we are covering. All right, we're covering those x's. But here's the other thing. Is every single x value sent to a unique y value? And for sure. I don't have x's being sent here to multiple x's being sent to the same y. So in that particular case, based on the evidence we see in the table, we do have a function. So I'm just going to go down here and I'm going to say, yes, this is a function. All right. Now, function notation is going to look very, very similar to y equals mx plus b notation. So we've got y equals mx plus b. We already discussed in the prior problem. That's y equals 5x plus 2. Now here's what function notation looks like. Slight difference. All right, I'm going to get rid of the y, and I'm going to write f, and then in parentheses, x. And what that means, ladies and gents, that right there, that little bit of symbolism, that means this particular equation is a function of x. So when you see that, we call that f of x, and we're abbreviating that as a function of x. Now, function notation has its advantages. Function notation tells people, hey, I can put something in, and I can very, very quickly evaluate and see what I'm going to get out. Okay? Here's an example. I can say, for example, I can put in 2. Instead of putting in an x here, I can put in 2. And what is that going to look like in this particular problem? Well, I'm going to replace the x with the 2. And I'll do a little bit of math. 5 times 2 is 10. 10 plus 2 is 12. So in this particular case, when I put in 2, I get out 12. Now, does that check out? Sure it does. Check out back up here. When I put in 2, I got out 12. And there's an advantage of function notation that we don't necessarily have as cleanly in slope-intercept form or y equals mx plus b notation. Let's keep on keeping on. We're going to go ahead and check out a couple graphs down here in 2-13. All right. Describe how the pattern grows and how many tiles are in figure 0. X represents the figure number and Y represents the number of tiles. Write an equation that relates X and Y, and then decide if it's a function. Here's what I'm going to go ahead and do. I'm going to do A, and I'll let you guys pause and tackle B and C, okay? So let's check out A together, and I'll zoom in. If you have this technology available to you, go ahead and use it. Otherwise, sketch this in quickly on a sheet of graph paper. It's going to work pretty easily there. But in this particular case, as I'm checking out A, I find it helpful with a graph. This is not an equation anymore. Not yet, anyway. I find it helpful to draw in something called a slope triangle. And a slope triangle is simply just going to identify 2 dots on your line, 2 dots that cross through nice gridded points like the ones they identified here, and talk about how you move from one dot, usually the leftmost dot, up and over to the rightmost dot. And in this particular case, it's clear that I had to count up 2 boxes and I had to count over 1 box. Now that's pretty telling, because that means for me, my slope is 2 over 1. And we've got this thing we'll develop here in a moment called, rise over run, change in y over change in x, but my slope is 2 over 1, up 2 and over 1, okay? The other particular thing I'll need is my starting value. And my starting value, I'm going to choose just a different color for this. My starting value is where I cross the y-axis. And that point is specific because that's when x is 0, right? That's my 0 figure, right? So when x is 0, where am I on the y-axis? And in that particular case, my start value is 3, right? Because on this line right here, this line crosses right here at 3. And that really tells me everything I need to know. Y equals blank x plus blank. Oops, not blank. There we go. Y equals blank x plus blank. And now I can fill these items in. Y equals, my slope is 2 over 1, that's 2. And plus 3. Now here's the other thing. All right, I'm going to have, in this particular case, a function. And some of you might be questioning, hey, Anderson, why do you got a function? I'm going to do my darndest to just tack in a vertical line here. There's my vertical line. And I'm going to throw out there, I'm going to claim that I can use the vertical line test. And I can take that line, and now I can drag this particular vertical line everywhere I want over the graphed line, not the axes, but the graphed line. And does it ever touch the graphed line in more than one spot or in 2 or more spots? And the answer is no. So we would say, yes, this thing is a function for sure. Yes. And if you were ever asked to prove that or validate that, you would say something like it passes the VLT or the vertical line test. That's how you could justify that claim, okay? Go ahead and pause this video now and try B and C. But ladies and gents, if you're ready to keep on keeping on with me, you can go ahead and we can talk about one more question here in 214. We got a similar, very, very similar, in fact, problem. We're going to be using a slope triangle to investigate that growth rate, and we're going to then go ahead and figure out how we can take this down into a unit rate. I don't really care about the equation in this case. I can't see the starting value, but I can see that slope triangle. So let's go ahead and check this one out. That slope triangle, like I said, we'd start here and we'd go here. We'd move from that left point to that right point, and it looks like here we go over 3, right? That's this plus 3, and the scale might confuse you a little bit, but we're told we go up 27. Very, very important. We put the rise on the top, the rise over the run. Now, the slope in this particular case, we could identify as 27 or up 27 plus 27 over 3. And if you left your slope that way, it'd be fine. For every 3 you go over, you go up 27, or for every 27 you go up, you go over 3. But most of you guys are going to realize that 27 is splittable into 3 pieces. And so you can also write your slope in a reduced form, like either one of these things, right? You could say, okay, 27 divided by 3, hey, that's 9, right? Calculator will validate that for you. Or you could reduce it by taking a factor of 3 out of top and bottom and rewriting it as 9 over 1. And that tells you that in this slope triangle, there's going to be 3 other little itty-bitty slope triangles where you go over 1 and up 9. Okay? And the slope triangle with a base of 1, right, answers this particular question right here. How many tiles are added each time the figure is increased by 1? You now have a unit rate, right? And that's going to become very, very important as we get later on in our chapter 2. But that's a pretty important skill. And if you're not 100% convinced how I got that, just go ahead and fire 27 divided by 3 into a calculator and check that out. It's not always going to be a whole number, but in this particular case it is, right? The last thing I'm going to ask you guys to try and goof around with is going to be something like this. All right, in 215, we've got a tool that's in this problem, and I'm just going to kind of expose you to this tool, and then I'm going to talk about review preview real quick. The tool requires something called Desmos, and if you go into our ebook has this in here, and it's got a tool that's built in here, and it allows me to adjust alpha and beta. Now, alpha and beta are simply, what's it called? Changes in Y and changes in X, right? Nope, I'm sorry. Not changes, there we go. Okay, and they're really going to allow you to manipulate the steepness of the line and check out some of these things that's happening. And first of all, it's always going to give you the slope, which is kind of a big deal. But see if you can use that to answer these questions here about this particular graph, and maybe you don't even need that. Maybe you can just do some counting there, right, to answer or tackle 2-15. All right, real quick, because I'm running out of time, let's talk about our review preview here. Our review preview is right here at the bottom, 19, 22, and 24. Folks, thanks for watching. Have a great day.